Okay, so good morning, everyone. So yesterday we were discussing about the physically unclonable function, and we talked about how the physically unclonable functions can be designed and how you can change the channel response pair by changing the inputs to the multiplexer or by changing the type of ring oscillator which we have here in the chain. There are other factors which decides the quality of the RO puff or any kind of puff. Like I was talking about, the variability play a major role in deciding the challenge response pair. At the same time, maintaining the reliability is really very important. The keyword reliability is bit tricky here in terms of the puff, because if I'm talking about reliability, it means that there should be no variation. There should be no impact of the process and temperature or the supply voltage variation in the circuit performances. But here we are talking about, here the meaning of reliability is there should be some process variations, but there should be no change in the responses because of change in the temperature or change in the supply voltage or change in the elevated, like change in the time where we are going to execute it. Like I was talking about one keyword, that was the negative bias temperature instability. That is one of the reliability concern. And that reliability issue, generally what happens, because let me give you the brief introduction about the NBTI, because that is really very important reliability concern which affect the performance of transistor or affect the performance of devices or the circuits with time. So that is really very important. At the zero time, there is no impact of NBTI, but we keep on using the devices, or if we keep on using the circuits, the impact of NBTI keep on increasing. What happens in that? A brief introduction or brief concept of NBTI is like, let us assume I want to create a silicon dioxide, SiO2. I want to create a MOSFET. So I have a bulk silicon. On top of it, I have to create a silicon dioxide. So you know that I have a silicon, then I need to create a SiO2 so that I can make oxide, and then I can create a metal layer, okay, or polysilicon. So to create the silicon dioxide on top of the silicon, you have to oxidize it. Oxidation is one of the process that is required to create the SiO2 layer. Okay. Now this oxidation can be of two types. One is a wet oxidation, and second one could be the dry oxidation. Especially for lower technology, wet oxidation is recommended. Okay. Now let us assume the wet oxidation is there. It means that the H2O will be there. Water will be there. H2O means we are utilizing the H2O with the silicon to make it oxidized. So if I am oxidizing the silicon, so oxygen particle, some of the oxygen atoms will be bounded with the silicon, and they will create a SiO2 layer. But because we are utilizing the water where H2O is there, some of the hydrogen particle may also be bounded with the silicon, and they are loosely bonded. They are not the strong bond, just like oxygen bond, oxygen or silicon, SiO bond. Okay, so this kind of bonds, we can call them the dangling bond, or they are loosely bonded. Now what happens if we keep on using the devices? So those dangling bonds, which were the part of oxidation process, might be they can break and they can tunnel into the oxide, and because of this tunneling, they can change the threshold voltage or operation of the devices. So there are two kind of changes. One could, let me open the slide, okay? So that, wait a minute, okay? So I'm switching from here to there, but I think reliability concept is important, okay? To learn before we understand the impact of NBTI in the security. This is really very important term, NBTI, that will also be utilized in the counterfeiting. Okay, so how that will be utilized, I will tell you. Okay, I'm directly going to that slide. Even I have the complete slide on reliability, but I don't want to take that part. If you like, I can take tomorrow, no worry. Yeah, okay. I'm sure you don't like it. Huh? Okay, so It's not coming. Control L is the shortcut key for the full screen, right? Not getting it. Can anyone help? Full screen mode? Can anyone help how to make it full screen? Because Control L is now it's working. Okay, I think there was problem in the. Okay, perfect. So let us talk about what I was talking about, the BTI or bias temperature instability. So basically, I just told you, like, if I want to create a dielectric or SiO2 layer on top of this silicon, so some of the atoms will be bounded with the hydrogen, and they are the loosely bonded. And if we increase the temperature, or you're utilizing your devices for longer, then these loosely bonded can be broken down and they can turn into the oxide, and they can change the threshold voltage of the device. So basically, this BTI, which I'm talking about, bias temperature instability, they can impact in both kind of devices, whether it is a PMOS or in NMOS transistors. But the impact of BTI in the PMOS transistor is more severe as compared to others. So ultimately there are two kind of BTI. One is the positive BTI and the second one is the negative BTI. Positive BTI, like we call it the PBTI and the NBTI. So there are four major components: NBTI in PMOS, NBTI in NMOS, PBTI in PMOS, and PBTI in NMOS. But out of all these four components, NBTI in PMOS transistor is more severe. Okay. So because of that, I have already told you, they are major concern if the oxide thickness is less than 2 nanometer. Okay, so they get more chances to tunnel into the oxide, and they can impact the performance of devices. Okay, now ultimately, what is the outcome of this one and how that happens? So basically, there are two reasons for the negative bias temperature instability or that reliability concern. I don't know how much close it is, but yes, try to understand. I'm assuming you all are from VLSI or semiconductor, so you must be knowing about the semiconductor physics. So let us try to understand what is the concept of NBTI here. So there are basically two reasons. The first reason is if you are utilizing your devices at elevated temperature, means higher temperature, then the probability of tunneling will be more. Okay, this is the first thing. And the second thing is if you have applied negative gate to source voltage. So let us assume I am trying to let us try to figure it out how it works. So let us assume I have an inverter. In inverter, generally the source terminal of the PMOS, normal conventional inverter, the source terminal of PMOS transistor is connected to the VDD. Drain of both the transistors are connected to the output node, and the source terminal of NMOS transistor is connected to the ground. Now, let us assume I have connected logic 0 to the input. What does it mean? Gate of both the transistors are at logic 0. Okay, and source of the PMOS transistor is at VDD. So the VGS here is minus VDD. Okay, so this is one of the case where any of the transistor they are under stress condition. And if the transistor is under stress condition, they can experience the negative bias temperature instability. So generally there are two things I have already written here. If the negative gate to source voltage is applied, it means that if in the logic circuit, if in the inverter you have given logic 0, the circuit will experience the stress condition. Okay, but when we remove or when we change the polarity of input, like if input becomes logic 1, then the VGS will become 0, and now the transistor will move into the recovery phase. Okay, so in NBTI, basically there are two kind of concept. One is the stress and the second one is recovery. Stress condition will happen if you have negative gate to source voltage, and the recovery will happen if you have changed the polarity. Okay, so let us assume my transistor is under stress. Then there are many impact on this. I have already told you what happens. They tunnel into the oxide and they change the threshold voltage. So this is what the NBTI effects are. Like whatever the SiH bonds, loosely bonds were there, they used to tunnel into the oxide. So that phase we can call them the NBTI stress. And similarly, if you change the polarity, like gate to source voltage becomes 0, then the phase we call it the recovery phase. Okay, but the important thing is it is not necessary that whatever the charge were trapped in the oxide during the recovery phase, they will come back again. So 100% recovery is not possible. So there is always a small permanent shift in the threshold voltage. Okay, so yes, of course you can recover it back, but 100% recovery may not be possible. Okay, so there are two kind of stress. One is like, because of that there is a permanent shift in the threshold voltage, and there is like temporary shift in the threshold voltage. So the permanent shift is because the particles which cannot be recovered back, they are responsible in creating those permanent shift in the threshold voltage. Now see the seriousness of this one, what is happening. Let us assume if the permanent shifts are keep on increasing with respect to time, even though there is a recovery phase, but I am not able to recover them all. So what will happen? With the time, threshold voltage of your device will keep on increasing. And if the threshold voltage of your device will keep on increasing, delay of the circuit will be higher. You know that there's a relation between delay and the threshold voltage. Okay, so I'm giving you a direct relation. What is the formula and all those things, you all know that. Okay, so what will happen if the transistor will experience the stress, or there is a permanent shift in the threshold voltage, that will impact on the performance of the device. Okay, so this is what is happening with your electronic devices. With the time, they slow down, they started slowing down. This is so NBTI is one of the reasons why your devices are being slowed down with respect to time. With the time, that is why the company used to give 3-year or 4-year warranty, because they know that up to 3 years my device is going to work properly, and after that you have to throw in the junk, and then that counterfeit comes into the picture. Okay, I will come to that point again, like what counterfeit is, how to detect that one, how to solve that problem, I will tell you. Okay, so I hope you understood what is the negative bias temperature instability and how that is creating a reliability concern. Okay, so based on the discussion what we have done as of now, we are thinking that the NBTI is a problem. Is it? That looks like a problem. But let me give you the solution of this one. Let me give you the positive side of negative bias temperature instability. What is the positive side? Yes, that depends on the many factors. It depends on what temperature you are considering, how much time you are putting the stress, what is the oxide thickness, what is the voltage you have applied. So all these parameters decides the rate of dangling bond defects. Okay, so how much penetration will be there, how much charge particle will penetrate into the oxide, that completely depends on various factors. How much voltage you have applied, what is temperature, stress time, oxide thickness, and what is the dielectric constant, and all those things. So these all factors decides the probability of dangling bond defects. Okay, so this is very, very important graph that give you the relation like oxide thickness, temperature, voltage, and all those things. Okay, so what does it mean? Let us try to summarize few things. I just told you, if I have a negative VGS, then my transistor will experience the NBTI. Now, let me give you the problem statement. If I am using my circuit in the normal condition like super threshold condition, or in normal conditions, so I will have some voltage around, let us assume if I am considering 65 nanometers, so 1 volt approximately supply voltage I will be applying. Okay, now let us consider the case if I am operating my circuit in sub-threshold conditions. In sub-threshold condition, we are reducing the supply voltage. If I am reducing the supply voltage, what it means, the effective VGS is going to reduce. Is it? If effective VGS is going to be reduced, then what it means, the effect of NBTI will be less. Okay, so the key takeaway is, even though the subthreshold circuits are problematic, especially if you want to achieve higher performances, but they are good, especially if you want to overcome the impact of the negative bias temperature instability. So if you are designing your circuit with low voltage, might be your electronic gadget can sustain for longer than the higher voltages. So this is one of the things. Second thing is, are you getting something new or not? Okay, I don't know, but let's try to understand the things. So this is one of the things. Next and very important parameter is, I told you there are two phases. one is a stress phase and one is a recovery phase. If you are keeping your circuit under stress for longer, might be probability of defect will be more. So the duty cycle of the circuit or of the input which you are applying also play a major role in probability of defects. So if you have very less duty cycle, means on time will be very less. If on time is very less, what it means, probability of stress is less, so the effect of NBTI will be less. So this is also one of the important. So there are many factors that decides, and also one of the parameter like temperature. If I'm using my circuit at lower temperature, the effect of NBTI will be less as compared to the higher temperature. Okay, so these are a few things that we should understand. Now, this is very important keyword that you should understand, like the threshold voltage shift increased by approximately 4% for each new technology generation. So what does it mean? It simply means that if I'm moving from 45 to 32, the probability of change will be more, or the percentage change in threshold voltage will be more in the lower technologies than the older one. So the NBTI becomes more serious, especially at the scale technology or at the lower technologies. Okay, so yes, but yeah, here is one catch. What is the catch? I just told you, because of the NBTI, the threshold voltage of device is going to increase. Okay, and then we understood that if the threshold voltage of device is increasing, what does it mean? It simply means that they are increasing the delay. Delay is going to increase. But on the other hand, you know that the leakage power is also related with the threshold voltage. The power dissipation is also related with threshold voltage. What it means? It means that if I have a higher threshold voltage, due to the NBTI, might be the power consumption by the device will be lower. So this is one kind of the benefit. Now it's your call whether you want to make it energy efficient or you want to make it high performance circuits. If your objective is high performance circuit, then NBTI is a problem. But if your objective is the energy efficient circuit, power efficient circuit, then NBTI can become one kind of benefit for your research. Okay, so here is like what you want to do. If you want to make like high performance circuit, definitely NBTI is a problem. But if you want to make energy efficient circuit, NBTI is kind of benefit. So there are a lot of paper the people have worked on. They have utilized this NBTI as a benefit for making the energy efficient circuit. So whatever the problem we are thinking in only one side, right? But flip the coin, you will get the benefit out of it. So this is what we call it Abdam, right? So we have to utilize it, like if you want to make it like energy efficient, definitely NBTI becomes one of the benefit. Okay, and the second is, yeah, so I've talked about like the degradation in drain current, so ultimately the power dissipation will be reduced. Okay, so with this one, keep these things in mind. Okay, and I will use this concept again when I will be talking about the counterfeited IC. Okay, so let us move again to the, I think, yeah. So that's it from the NBTI side. Again, let us move towards to the security part. Yeah, because this part was needed to understand the security one. Okay. People will be saying I'm jumping from here to there, right? But yes, because that was needed, that is why I'm teaching it. Okay. So, yes, I think this is what we have already covered in the previous lecture, okay, where we talked about the architecture of PUF. And this is the simplest architecture that we can create, but we can create even more complex architecture that depends like which kind of RO I have used here, what is the order of your multiplexer, what kind of counter I have used, whether I want to take output from the counter or comparator, or after summing up the counter values or subtracting the counter value, you can do any kind of modifications so that you can make good CRPs, good challenge response pairs. Okay, so this is what we have done. Yeah, I think I have already told you the challenges. And I talked about, yes, this is very important. Like this is the lower graph which I'm showing here is related to the NBTI. Because what will happen if the impact of NBTI is more, then they are going to increase the threshold voltage of device. And if they are increasing the threshold voltage of device, delay is going to increase. If the delay is going to increase, the frequency of your ring oscillator is going to reduce. Okay, so they are directly related with the frequency and the delay of individual inverter. So if any of the circuit, any of the transistor is experiencing negative bias temperature instability, what it means, ultimately the ring oscillator frequency is going to reduce. So ultimately, if I want to make a robust RO, to make a robust RO puff, definitely the impact of NBTI should be as small as possible, as less as possible. If the impact is less, what it means that these kind of things are desirable. So this is also very important. Let us assume if I have a 2-ring oscillators, the rate of experience of NBTI must be same or close to each other, so that even though they are degrading, but they are degrading with the same rate. So they will not create problem in the challenge response pair generation. But if one of the RO is degrading its performance with the faster rate than the other one, then might be after a certain period of time, they can give you the flipped logic or opposite logic. This is not recommended because we have already set the challenge response pair in the database. And once it crosses that threshold, might be you will get the wrong challenge response pair, and that will not work. Your puff is not going to work in this case. So ultimately, the first kind of characteristics is required for the ring oscillator, and the second one is not recommended. Okay, otherwise you will get the false challenge response pairs. So with this one, I think configurable I have already told you, so I'm not going into more detail. There are a lot of things that could be done. If you are interested, do discuss with me. I will tell you the new circuit topology, free of cost. Okay. So as of now, what we have seen that the RO puff is one of the way to have the hardware security primitives, but there are other way to design the puff as well. That we call it the arbiter puff. What is the arbiter puff? Arbiter puff also utilizes the delay kind of things. Okay, if you see the ring oscillator, they are deciding the oscillation frequency based on the individual inverter delay. Similarly, the delay is also decided here. Like, let us see what is happening here. The simple architecture of the RO puff looks like this one. Wait for a second. Let me explain everything. You will be able to understand what I'm saying here. Let us assume this is the simplest architecture. We have a 2x1 multiplexer in 2 rows, okay, and they are connected like zigzag here and there. So let us try to see here. The first multiplexer having 2 input, and both the inputs are given from the stimuli they have been initiated. But based on the challenge, whatever, so the control signal of the multiplexers are considered as a challenge. Okay, so let us assume if challenge is 0, in this case, whatever you are considering, this what the upper one will be selected, I0 will be selected, and this one will be selected. Okay, so this path is going to be here and here both. Similarly, whatever the response, whatever the challenge here, accordingly the path will be selected. So I know that designing a multiplexer, they have a logical gates. So if the path is like from here to here, they may experience a different delay than if they are moving from here to here and so on. So based on the challenges, might be they can select appropriate inputs, and accordingly their path will change. And if you have a different path or separate like different path for different challenges, definitely the delay will be different. So the signal which I am going to receive at this point from both the multiplexer will arrive at different point of time, at different delay. So let us assume if this output comes first, so that will consider as a trigger. That will enable your D flip-flop. And now, whatever the signal is coming, let us assume it is 0, so 0 will be passed to the D flip-flop. And similarly, if 1 is there, 1 will be passed to the D flip-flop. So the D flip-flop output can be 0 or 1, it depends which path I have selected. So this is how this D flip-flop or this arbiter-based puff used to give you the response, and they vary with the path. If I am changing the different path, I am utilizing the different path, definitely your response will be different for different kind of challenges. But the challenge is for the problem with the arbiter perf is uh, the challenge response pairs are less as compared to the ROPUF. Ultimately, that depends on the architecture. It's not like that one. Yeah, so let me give you some simple example. So let us assume the challenges are given like this is the structure. Let us assume challenge is 0, 1, 0, 1, so on. So if I have a 0, this first path will be selected. Okay, and here I have a 0, so this will be selected. So this is the I0, this is the I0 for this one. So in this path, this will be selected. And now because here is the 1, so red is one of the paths that is connected to the D, and green is one of the paths which is connected to the clock, and the path can change, and that depends what challenges I have given. So there could be the multiple possibility of path, and if you have a different path, definitely delay will be different. So whatever the signal you have initiated at this point, might be they can reach at different point of time. If the clock is reaching early, then the puff will be enabled. So whatever the previous value, that will be transferred immediately. So if the previous value is 0, 0 will be transferred, and if previous value is 1, then 1 will be transferred. Okay, and that will be considered as a responses. So this is how the simple ring oscillator based puff works, and how you can generate the responses from a particular challenges. If you have any question at this point of time, you can ask. Otherwise, we can move ahead. Arbitrage is nothing but is a D flip-flop. Okay, so if I am receiving the clock early, then it will enable, and then whatever the signal I have at the D, that will be transferred. If it is 0, 0 will be transferred. If it is 1, 1 will be transferred. Let us assume if input comes first, the input becomes 1, then it will wait for clock to be enabled. So in that case, your output will be 1. So response will be 1 if this signal is faster or this path is faster, and the response will be 0 if this path is faster. Okay, so this is how you decide the responses from the arbiter perf. Any other questions? Is it fast? I don't know. If it is fast, let me know. I will slow down myself. Okay, so let us move ahead. The third kind of the physically unclonable function is the SRAM based perf. Yes, we are utilizing the SRAM to make a perf to get uncertain responses. Let us see how it works. We know that the simple perf has this kind of structure. Okay, this kind of structure. If you see, if I am talking about the 60 transistors, like the conventional SRAM cell, the 6 transistors will be there. But in the latch, there are 4 transistors which are holding the logic. Okay, here if you see, there are 2 inverters, and each inverter requires 2 transistors. So total 4 number of transistors are there to make a latch. Okay, now I know that, we know that, not only me, everyone knows that if I power on the memory or SRAM, initially they are at the metastable state, and they can settle down to either 0 or logic 1. That depends like which path is stronger. If I'm assuming my both inverters are identical enough, so I need to put some force so that I can set to either logic 0 or logic 1. Because when I will power on, can I draw somewhere? Yeah, and let me write on the board. And I'm the teacher, I should write on board, right? That's important. Online people will not be able to see. Okay, so I have to draw this. Okay, so if I talk about the SRAM cell, the simplest structure of Okay, so this is the latch. Okay, here what happens? Initially, let us assume this is the VDD. If this VDD is equal to 0, so this particular latch is not going to hold the logic. It is visible from there. It's fine. Okay. So this latch is not going to hold any logic because if the VDD is equal to 0, there is no potential difference, so they cannot hold any logic here. Now when we power on, what is going to happen? Because both the inverters which I have here are identical enough. If they are identical, they cannot decide at which logic I need to hold. Because see, here I have an inverter, and I know the inverter property is if input is equal to 0, output is 1, and if input is equal to 1, output is 0. So this is the property of inverter. So if I power on, and assuming that both the inverters are identical enough, so I cannot say where my logic is going to be settled down. They will be at the meta stable. Okay, so in that case, in one of the side, either on left or right side, we have to trigger it to take decision whether I have to store logic 0 or logic 1. Now, even though I have decided my SRAMs are inverter in the SRAM are identical enough, but at the time of fabrication, what will happen? It is not necessary the property of all the transistors are identical. Okay, so let us assume I have fabricated 10 SRAM cells. In 10 SRAM cells, there is a possibility the left side inverter for 5 SRAM cell may be stronger than the right side inverter. This is possible. How that is possible? Because the threshold voltage may vary. If the threshold voltage is different, then their strength will change, and one of the side may be stronger than the other one. So based on that, if you power on, either they will set to the logic 0 or logic 1, depends which side of inverter is stronger. Okay, so this kind of variability at the time of fabrication of memory is utilized to consider to generate the responses from the memory. Are you able to understand what I'm saying here? That's really very important here. So memory can be utilized, or SRAM can be utilized to generate the responses. Okay, and they are completely in random in nature. Okay, when you power on, they will settle down to a particular value because one of the side is stronger. Okay, and then it's processed it, and that can be considered as a puff key. Okay, SRAM based puff key. So this is how, yeah.
If there is a noise in the circuit, it can pull it out of the metastable state as well.
Yes, that's possible. Correct. So I'm going to add one more thing here. Yes, very good question, and I was supposed to explain these things. Now, I'm just, as of now, what we have done. We have done like based on the process variation at the time of fabrication, we are deciding, okay, which of the path is stronger, which of the path is slower and faster, and accordingly I will get the responses. This is what I'm going to see. Like if I will apply some challenge, I'm expecting I will get the same responses because the device is already fabricated. Now, here the noise play a major role. What is our expectation? There should be less noise in any kind of circuits. Let us use it as a benefit. How it could. So I am here to explain whatever the problem you are thinking. I am trying to give the solution for that. Okay. So let us try to see if any noise is present in the circuit. Then what is the role of TRNG? The role of TRNG is if there is no noise, it becomes the PRNG. It will generate a fixed set of responses. Fixed set of key will be generated. But if noise is there, if I have added up a noise that is completely random in nature, so they will increase the uncertainty in response generation. And after adding the noise, your PRNG can become the TRNG. Okay, so here the noise signal which is present in the circuit can be utilized as a benefit to make your PRNG as a TRNG. Yes, it could be different. So one time, so you cannot generate the same key again, because the noise is going to change.
After get including the noise, I'm giving the response, challenge, and I'm getting the response at one side. After fabrication at everything, I'm going to check it again, like my IP.
That could be different. That could be different. So at the simulation, it could be different. At the fabrication, it's different because after fabrication, there could be some process variability and might be your response could be different. And if, yeah.
Many companies buying that chip and is getting the noise different at that point, then my challenge, my response is different at them. So how can I?
So for that, they need to add the fixed fixed kind of noises. They should know the definition of noise, which kind of noise they are going to add, so that they can create more uncertainties. But they should know, like, it's not like randomly I have kept the noise and then it will be generated. Then there is no validation point here. Yes. So here we are not utilizing the environmental noise, because environmental noise cannot be captured, cannot be analyzed, because they are completely random in nature. So here, forcefully, you have to generate a noise signal and you have to add into the circuit so that you can get the responses. So that you can get the reliable responses all the time, because you know what kind of noise you have added.
There are noise sources which we use to characterize.
Yes. There are a lot of noise sources. This is another scope. When time permits, definitely I can take lecture on reliability so that I can tell you what kind of noise sources could be there.
Question, like, if you go back to basically the ring oscillator based perf, like the way I simulate the circuit, like it may not get exactly fabricated like that. So now the delay that I was expecting in the slow corner, it may not come exactly as it is after the
Absolutely true. Absolutely
so
true.
challenge response pair lookup table that you made during the simulation may not match exactly when you.
So you have to create a lookup table after fabrication.
Oh, but you're assuming that, so for that you are assuming you will get a good chip and nobody has done anything with that particular chip.
No. After fabrication, that CRP is being generated to validate, to authenticate it. So let us assume I have fabricated. Let us assume I have asked a foundry to fabricate 100 chips. Okay, they have created a challenge response pair. They have the lookup table for all the chips. Okay, now because the foundry has directly given us the challenge response pair for all the 100 chips, and I know, like, okay, if I will apply this challenge, I will get these responses. Let us assume foundry, like the fab unit has created the 120 units, but they will give only 100 in the supply chain. So I can validate only 100 only, even though they have created the 20 more. There is no database publicly available, so they cannot be used. But even though they have fabricated 120, so this is how it works. Okay, so that's important. And this is one more concept which I'm going to explain later on. That is the metering one, logic metering, hardware metering. Hardware metering help in the same way. You know what challenge response pairs are, and we know how many chips I have ordered, and accordingly you can count, okay, I need to unlock these many chips only, because I know that I'm going to explain these things later on, don't worry. Okay, so there's my pointer. Yeah. Okay, so this is how the SRAM based perf is going to work, and we are going to generate the challenge response pairs out of it. Yeah, this is the logic locking. Yeah, hardware metering. Hardware metering is like, okay, so the designer used to design the things. Okay, they used to create the GDS. They used to send the GDS to the fab lab for fabrication purpose, and they have fabricated it and they have locked with some challenge response pair which I was talking about. Once they have logged it, they will send it to the actual user, and they know what the challenge response pair is. By utilizing the same CRP, they will unlock the key and they will use it. So authentic key has been given by the foundry after fabrication to the user, and because I have ordered 100 chips, they will give the 100 data set only, not more than that. So if some other person who has still that your chip, they don't have the CRP, they will not be able to unlock it, and that there is no meaning of that chip then. So this is what we call it the hardware metering, and here the CRP help us to identify whether I have received the correct chip based on whatever database I have or not. Okay, so this is what we call it the hardware metering. They can utilize this challenge response pair to validate the authentic chips or correct number of chips. Okay, There is one more security concern. I think yesterday someone we are talking about the side channel attack. What this side channel attack is, I don't know how much relevant to this program is, but yes, maybe interesting to know. Huh? I don't know. How is that? Is fine? Okay. So, let us try to understand what is the side channel attack, what is the importance of this one, and how this is one kind of security threat, security vulnerabilities. Okay. Basically, there are, okay, so let me first define what is the side channel attack. Side channel attack means like once the chip is being fabricated, okay, I have the setup, complete chip and everything. This is twofold. Yeah? So if I have everything, but the attacker may guess the information, whatever the information is being stored, they may guess the information based on the power profile, based on the delay profile, or after injecting some electromagnetic waves, they can extract the information, what information has been stored. I was explaining yesterday, if you have 8-bit register and they are storing a different bit of like data like 0 or 1, they will dissipate a different kind of power. And if they are dissipating different kind of power, it means that you can identify, okay, if I am getting the minimum power, it means that either it is logic 0 or it is logic 1. And if there is a range of the power dissipation, based on that, they can identify it. Okay, so let us assume if I have a total 8 transistor, total possible 8 SRAM cell in a register, total possibilities are 2 to the power 8. Okay, but it is not 2 to the power 8. There are a lot of possibilities where the same power dissipation I can observe. If 4 transistors are 4 SRAMs are logic storing logic 1 and 4 are storing logic 0, so there are n number of possible way where the 4 memory will store logic 1, because 1 1 1 1 0 0 is possibility, 1 0 1 0 1 0 1 0 is a possibility. So I will get reduced set where I can interpret what information has been stored. Okay, so this kind of things are being utilized to guess the information in the memory or wherever it is the data is being stored. Okay, so one of the way is like, yeah, the EM based side channel attack. They used to trace the pattern on the chip, and based on that they process it and they can guess where the logic high and logic 0 is. Okay, so this is one of the way. Second one of the way is the understanding or the getting information based on the leakage power. Forget about this one. Let me directly come to the actual concept, which is very simple to understand. Let us assume I have this memory. This memory is kind of 60 memory, 60 SRAM cell. If this is a 60 SRAM cell, now I'm assuming that the Q node is storing logic 1 and the QB is storing logic 0. Okay, and if this is the case, and let us assume my BL and the BLB are like VDD and the 0. Okay, if this is the initial setup for your memory, BL and the BLB are connected to the VDD and the 0, and I'm assuming that my Q is equal to VDD and QB is equal to 0 here. Okay, so if this is the case, first case, in this case, these many leakage current or subthreshold current will flow through it, because ultimately to flow the subthreshold current, definitely there should be some potential difference between the source and drain terminal. Okay, so if I'm assuming my Q is equal to VDD here, this is the VDD, this is the VDD, there will be no current flow through this device because they are at the same potential. If you see here, if this QB is equal to 0, I'm talking about this blue curve, blue one. If QB is equal to 0, here is the VDD, here is the ground, there will be some subthreshold current flowing through the M6 transistor. Similarly, if you see here, BL is VDD, Q is VDD, there is no current flow because they are at the same potential, and there will be no current flow through M2 transistor. Similarly, for all other transistors, you can see what is the potential at source and drain. Accordingly, you can decide whether there will be some subthreshold current flow or not. If there is a potential difference between source and drain, definitely some current is going to flow. Now properly see this particular curve, this particular circuit. I can have two possibilities. Either my memory can store logic 0 or my memory can store logic 1. So here I have two cases. The first case is if my memory is stored in logic 1, in this case, these many subthreshold current I am going to observe. And if my memory is storing logic 0, so there are 4 leakage current components which are flowing through the memory. Now, because there is a difference in the leakage current components, the power dissipation in both the cases could be different. The leakage current flowing through the circuit could be different if I am changing the logic. If this is the case, the leakage current distribution or power distribution of this device, yeah, you can sum up, might be they can scatter, if I apply the Monte Carlo simulations, might be for logic 0, they are scattering here, or they are scattered near to this mean value, and might be for logic 0, they can scatter to this mean value. If this is the case, the attacker will be able to guess, even though after applying Monte Carlo simulation, they are seeing a sufficient difference in the distribution of power for logic 0 and logic 1. And based on that distribution, the people can guess what information you have stored into the memory. Any problem here? Now, how to solve this problem? To solve this problem, the only one way is if somehow I can equate the number of leakage current components. If somehow I can equate the leakage current components, if the leakage current components are same in both the cases, the possibility or the scattering or the variation after applying the Monte Carlo simulation will overlap to each other. And if they will overlap to each other, yeah, might be you can add some. This is one of the topology which was published in TVLSI in 2018. Okay, and here they have used 2 always off transistors to increase the subthreshold currents. Okay, so now in both the cases, the number of leakage current components are same. If the number of leakage currents are same in both the cases, like while storing logic 0 and logic 1, the distribution will look like this one. And if the distribution is like this, even though they got the power profile, scattered power profile, they will not be able to guess what information you have stored, because the Monte Carlo distribution or the histogram is overlapping with each other. If they are overlapping with 100%, you will not be able to guess what information you have stored into the memory. This is very simple but very effective technique to prevent your memory from the power-based side channel attack. Okay, so that's really very important to understand, like what is happening here. Yeah, we have published a number of work related to the same area. Maybe you can explore the things what we have done. Okay. Any question at this point? Online audience? Any questions? In chat box? I think I'm encouraged to ask the question. One-way communication is not good. Okay.
So like I can see that when the means are different, in that particular case, the difference is just 1 nanoampere. Is it possible to accurately detect 1 nanoampere?
Yeah, that's possible. That can be detected. So they will be able to clearly see the differences in the power patterns.
Yeah, that will just 1 nanowatt or something.
So that is fine. Even one picowatt can also be detected. There are a lot of the tools where the nanoampere current can be differentiated. That's possible. Okay. So what they used to do, they simply extract the information of current and all those things, and they draw the patterns. Okay. And after drawing the patterns, they are seeing the variation. Peak is going to change, even though a small peak, even picosecond peak, picoampere peak, they can identify, okay, here is the peak, this is the different than the second one. So they don't want exact number, they just want how much variation. If a small variation is there, they will be able to guess it. So what they will do with the power? No, they are not interested in power. They are interested in tracing the information. If there is a variation, they will detect the variation, like they will say, okay, this is logic 0, this is logic 1, or opposite.
In that case, you are trading off the area of the SRAM, right?
Of course. Yeah, nothing is free here, right? So you have to pay either in terms of area or in terms of latency or in terms of power. Always you have to pay in terms of something. You cannot get all the benefits. If you are getting all the benefits, you are doing wrong thing then. Okay, and this is true. Fine. So this is the side channel attack, like a power-based side channel attack that you should understand it here. Okay. Okay. Hardware Trojan. Someone was asking like, what is the hardware Trojan? I'm touching all these security threats, security concerns in single slides, so that at least I should give the flavor what this kind of security concerns are, so that wherever you are interested, you can explore yourself. I think I have already told you the Trojan, right? Hardware Trojan. What is a hardware Trojan? At the time of design, there is a possibility designer can add the additional module, okay, into the circuit without my knowledge, and they can trigger at specific conditions or rare conditions. They will not be enabled in the normal condition like 0101. So if they will be enabled in the normal condition, they will create a problem. But they will try to find in some specific conditions like a particular temperature, particular supply voltage, particular time, or whatever. At that point of time, your trigger will be enabled, and might be it can give you the wrong logic. Okay, so the hardware Trojan, recently the reality is the hardware Trojan concept is completely based on the hypothesis. Most of the research people, what they are doing, they are inserting the Trojan, and now they are detecting the Trojan. In reality, long back in 1970s, some Trojan were detected, but recently there is no real report that Trojan has been inserted into the chip. But there is a possibility people can do that. Okay, even engineers are doing crime, right? So, and Osama bin Laden was the engineer, right? So that's possible. So, drones, you are going to create, civil is fine. He was engineer. I believe on engineering. There is no like civil or electrical or electronics, right? Engineer means engineer. How I can believe that you are the constructor? You can be. No. What is the relation of electronic with the destroyer and the constructor? Okay, so there's no hard and fast statement like who is the creator and who is the destroyer. Okay, so if I'm talking about hypothetically, the Trojan has been inserted. Okay, so the Trojan is basically, I told you there are a small module that has been added into the design without the consent, without the knowledge of user, and they can activate at a particular conditions, particular time, and that the designer will decide like how that will be enabled. Okay, and that can create a problem. If you see, there could be a lot of things like they add, like let us assume I have millions of transistors. Okay, if I have a millions of transistors, if I have added 10 transistor just to make a Trojan, it does not hardly matters in area overhead. If I have the millions of transistors and 10 transistors I have added, no one is going to check like how many additional transistors you have added it. Okay, because the area overhead is very small as compared to the million of transistors. Similarly, so if the Trojan can be the physical one, they can create this kind of things like if whatever the wire I have, if they have nicked the wire like they have make it thin, and might be if the load increases, that wire can be broken, and might be the Trojan will be enabled. That's also one of the possibility. So let us assume I know what is the power handling capacity of your wire or interconnects which you are using. Now, if you have reduced the thickness and the width of your interconnect, definitely it will work on the normal condition. But if it is working for longer, the power dissipation will keep on increasing because heat is increasing. Because there may be some finite resistance will be there. Of interconnect resistance is always there. If resistance is there, heat is going to generate. Might be they can broken, and your trigger or a Trojan will be triggered. That's also a possibility. Also, there is possibility like they are using different kind of material. Might be I was talking about the NBTI. They know that if Let us assume my threshold voltage was 0.4 volt, and they have enabled the Trojan in such a way, if the threshold voltage reaches to 0.42, then my Trojan will be enabled. And 0.42 threshold voltage can happen due to the NBTI effect. So maybe after 2 years or after 3 years, my threshold voltage has reached to the 0.42, and your trigger will be, your Trojan will be activated. So at the time of purchasing, at the initial time, there is no NBTI effect, you cannot detect it. Because that will happen after 2 years only, after 2 years of your use. Okay. So this much of serious things are on hypothesis purpose. Like hypothetically, these are possible. Okay.
There are reliability simulations as well, I believe. Like they should be able to detect this.
How reliability will be detected? Let us assume I have made a circuit which is NBTI tolerant. Okay, and let us assume if there is some NBTI impact, and they have added one extra transistor. So what is the relation of reliability of? So let us assume I have added 2 XOR gate.
I was talking about that, nick the wire.
Yeah, that's possible.
Yeah,
that's possible. Yeah. So this is at the time of fabrication in the fab unit. That's fine, and it's also very important. Like whatever the scheme you are using for the fabrication purpose, it is very difficult to manipulate those things. Okay, so hypothetically everything is possible, but in reality they are completely automated, and modifying your mask is very tricky job. Okay, so that's very important. So fake and counterfeit ICs. So there are many things, like they can connect the additional wire here and there, which is not impacting the real cases, but might be in some cases they will be enabled. They can enable your Trojan, and that can create a problem. Okay, let us try to consider a few of the smallest circuit to understand more about the hardware Trojan. Okay, so let us assume, yeah, there are some way where the Trojan can be inserted. Okay, so intentional mistakes in doing the designing the specification, this could be one of the concern. Malicious IP core has been used. This could be one of the source of security threat. So manipulated tools, whatever the tools you are using for synthesis, placing, routing, and everything, if you have changed the process, might be the outcome could be different. So there are various ways at each stage from idea to fabrication, there is a possibility of modifying the things. Okay, so it is not like you cannot detect directly, like, okay, the problem is at the specification or problem is at the design. It can be done at any stage. So detecting those things is really very tricky job. Let us try to understand a very small circuit like this one. Actual circuit, let us assume actually I have a OR gate, NOR gate. Actually I have a NOR gate, and if I will give 0, so this is actual, A and B are the input and C is the output. This is what actual circuit which I need. Okay, but the designer has added 2 additional things like a trigger and the payload. What is the role of trigger and payload? I will tell you. So let us assume 0, 0 is there. If 0, 0, then what is going to happen? This is going to be 1, and 0, 0 means here I will get 0. If the XOR input is 0, so they will act like a buffer. They act like a buffer. So if these kind of things are not there, for 0, 0, I should get C is equal to 0. C should be 1, and if this is 0, this will pass the same logic, and because I have the buffer, so I will get the same logic. So I'm not getting any change in the output. Similarly, if it is 0, 1, it is the same thing. 1, 0 also the same thing. In only one condition, Trojan is going. Okay, so because we have considered only 2 inputs, and only 25% chance is there your trigger will be enabled. Rest 75% time it will not be enabled. Okay, so this will, like, if 1, 1 is there, this trigger will give you 1. If this is 1, this XOR will complement the logic, and now C modified will become 1, will become 0. So here you was expecting the C should be 1, but you are getting 0, or the vice versa. So So this is how the Trojans are being enabled. Like the trigger, they trigger the payload. Triggering means like the logic which is triggering your outcomes. Similarly, let us go into more complex, little bit more complex to understand more in detail. Like, so let us assume if I have a 4 inputs and the structure is something like this, the black part is the actual one, actual circuit which you have, and the red part has been added into the circuit. Now try to see at which combination your trigger and the payload will be enabled. Okay, so there are very less, like if I have 4 inputs, so total possible combinations are 2 to the power 6, 2 to the power 4. That is 16 combinations. Out of 16 combinations, there are only very few combinations when this will become 1, this will become 1, then only I will get 1 here. And to make 1 here, what I need, either of C or D should be 1. If C is 0, 1, 1, 0, whatever it is, like if they are 1, 0, 0, 1 or 1, 1, it will give you 1 here. But if D is 0, then again it will not work because this is not going to be enabled. So they again reduce the probability. So only there are 2 possibilities where your Trojan will be activated. So out of 16 combination, only 2 cases where your Trojan is activated. So you can see the probability 2 by 16. No, that also depends on this logic at this point. This is the AND gate, na? So this AND gate will trigger only when here is 1 and here is 1. That is fine. That is fine. So D is actual input to this one, actual circuit. But from here I am taking the output of this OR gate and they are connected to this one. So if this OR gate is giving 1 and D is 1, then only your trigger will be enabled. Yes, it is connected. Huh?
He's saying the trigger is dependent on D. The moment the D is equal to 1,
Huh?
the red upper path to the trigger gate
Huh?
will be 1 and the bottom path.
Well, this is the AND gate, na? AND gate means like this, both the inputs should be 1.
Just the C and D are the input.
Huh?
So the moment the D becomes 1, the output.
Yeah, of course, yeah. So it depends like how complex trigger you are designing. I am giving the simple example to understand how this works. But yes, you can make it more complex, more rare cases you can find where it should trigger. So that I should not be able to detect what is happening here. They are easily detectable. But yes, this is just to understand how it works.
One more question, like the verification team will be able to catch this.
Of course, they will be able to do that if the circuit is very small. But if they have large circuit, it's still like now testing is really very important. Verification will verify the logics in circuit and everything. Testing team will do the testing for all input patterns. Now let me give you the simple example. If I'm trying to test a chip, okay, and with the frequency of 1 gigahertz, okay, let us assume clock frequency is 1 gigahertz, and you have 10 inputs. So total number of possible cases could be 2 to the power 10, okay. So if the clock frequency is 1 gigahertz, total possible combinations are 2 to the power 10, okay. So can you tell me how much time is required to test for all the cases? Just calculate it. You will be surprised. Calculate it. Do the exercise. You have 10 inputs. Total possibilities are 2 to the power 10. So these many input patterns you have. And if you consider your frequency, clock frequency is 1 gigahertz. So for 1 gigahertz means 1 nanosecond delay is required, like 1 nanosecond time period is there. So for one pattern you need 1 nanosecond. So 1 nanosecond into 2 to the power 10, what is the time? Huh?
1024 into 1 nanosecond.
Why 1024?
2 to the power 10. So 1024.
Yeah, 102. Oh, yeah. Calculate it properly. So tell me, like, to test all the patterns, 2 to the power 10 possibilities, how much time is required to test all these cases? Huh? Okay, microsecond. Now I have changed my input from 10 to 20. 2 to the power 20. Hmm. 2 to the power 20 will be the last time. 2 to the power 20 patterns means, huh? Calculate it properly. Calculate it. Do proper calculation. Huh? Hmm. Millisecond. Now let us assume we have more number of inputs. So if you keep on increasing the input, might be to test all the patterns, you may take more time to do that. Might be to test all the patterns, you need some years to test your chip. So if you are putting your chip to test for 2 years, even with this high clock frequency, there is no meaning of your chip. So that's very difficult to test all the cases. So then testing team play a major role. Test and testability course is there, how to test with the rare cases. Okay, so I'm not going to in more detail. That's really very important to understand. Okay, as of now, we have seen many good things. Let us talk about the serious thing. Okay, this is also one of the serious concern. What is that? The global e-waste, which we are doing every day. Huh? कितने मोबाइल फेंक दिए अभी तक? Everyone must have thrown at least 2-3 mobiles in last 3-4 years or last 5 years. So these many electronic waste we have created. And this is the statistics which we can see here. What is the statistics? If you see, the 80% of the e-waste is not being recycled. There is no document where they are. They are thrown here and there without any processing. Only 20% are being documented, collected and recycled. And out of this, if you see, this is the portion like from where they are coming. 38% they are coming from small equipment, 20% large equipment, 70% or some temperature exchange equipment, all these things, screen, small ITs and lamp and all those things. So these are the percentage of contribution of your the whole electronic waste. But out of that, only 20% are being recycled, 80% are not being recycled. Is this a serious concern? Yes, of course it is. So before throwing your mobile, before buying a new mobile, think, can I run it for 1 more year? If yes, do it. Otherwise, throw it in the garbage. Who cares about the nature? Okay. So ultimately, out of this 80% which are undocumented, uncontrolled waste, the 76% we don't know where we have thrown it. Ultimately, what we used to do, let us assume if my mobile is not working, so there are two ways. One thing I used to keep in my at my home. Second thing is I used to throw in the dustbin. The third thing, okay, if I will throw in the dustbin, someone may steal my phone and they can get my data. So to be myself more secure, I will throw in the river. Huh? That's possibility. No one is going to extract my mobile phone from there. But have you really recycled my electronic waste? No. We have created a question mark on environment, on nature. Okay. So these are undocumented and which are one of the serious concern. Okay. So on positive side, there is a huge scope for electronic waste industry. If you can run your own electronic waste industry like a startup, might be there is a huge scope, because day by day electronic wastes are keep on increasing. The rate of increment or use of electronic wastes are keep on increasing. So someone who are interested in startup, definitely they can do that. They can recycle them, they can counterfeit them. Huh? That's also a very important thing. Okay. So this is not recommended, it is an unethical job, but yes, generally the counterfeited ICs are utilized in the repairing shops and here and there, where with a low cost they can change your module and you can use it. Okay. So with this serious motivation, let us try to move ahead how they have been done. Bored नहीं हो रहे हैं आप लोग? It's fine. Are you getting bored? No, I have a lot of good things to speak. Okay. Okay, fine. So here is some dark secret of the counterfeiting IC. What they do? 80% electronic wastes are not being recycled. 20% are being recycled. How they do that? We are throwing our garbage, like our electronic waste like this. The people, they used to collect the scrap. They sort them by their size. They remove the components. They sort it and then reprocess it like a fresh, rebranding it, and they add into the supply chain. Now here is the problem. I was talking about these things yesterday. If the counterfeited ICs has been added into the actual supply chain, if they are being sold like a new chip, like a fresh chip, how you are going to detect those things? Now remember the NBTI. Okay, I just talked about NBTI is a problem, especially if you want to make them reliable. What is the concern? The threshold voltage, there is a permanent shift in the threshold voltage of the devices. If any chip is being used for 2 years or 3 years, there must be some permanent shift. So I know the data sheet of actual chip, new chip. Simply what I have to do, I have to plug the actual chip, new chip, in the counterfeited chip. If there is a parameter variations, I will say, okay, this is the counterfeited IC. So here, NBTI becomes the benefit. NBTI can be utilized as a detection scheme, counterfeiting detection scheme, counterfeiting detection techniques. Huh? Yes, of course you can validate them. So it's not about whatever the problems we are thinking, we are seeing, what we are generating, they are always a problem. There could be some solutions out of those problems. Okay, so this counterfeited IC can be detected by using the concept of negative bias temperature instability. So if I want to avoid the counterfeited IC, I'm expecting there should be more NBTI effect in the circuits, more NBTI effect in the devices. Okay, but the actual problem comes where, let us assume I am the end user, okay, and once I have used it, there may be some of the component may not be working. I remove that board, throw in the garbage, and the people must have, like a e-waste, they must have processed it. Once they process it, they add into the actual supply chain, global electronic market in the supply chain, and might be you can get back your own chip back to the end user. And this is a serious concern, especially your application is a mission critical applications like space, defense, and here and there. You are expecting your whole system should work for 10 years, but because the used IC was already in use for 5 years, might be your system may fail after 5 years. So that's really one of the serious concern, and the proper detection is required. This is a question mark on this. Huh? Okay. Yeah, so in reality, if you talk about, yeah, this is very old data, but still, if you can see the incident reported by the international something like, I don't know the full form, I was knowing, hardware sources, international hardware source, something like that. They have reported like the number of counterfeited cases are keep on increasing day by day. In most of the cases, major contributor are analog ICs. Okay, analog ICs are the major contributor, like 25% processor, then memory, logics, transistors. So they are being counterfeited and they are being reported. Okay, this is a source, you can look into that, what is happening here. Okay, now here is the summary. Even though I have not discussed about what is the PBT variations, but everyone knows what those things are. Let us try to understand what good things we can take out of the bad things. Okay, so see here. Here are some, okay, I need to switch. Okay, okay, fine. So here is the things. What things we have here? There are few variations like process, noise, temperature, supply variation, aging effect, radiation effect. If all these things are there, if you see in the normal logic design, I'm not expecting there should be no process variations. So if there is a process variation, it's not a good thing. It's ugly. But yes, other things are also bad. Like in normal logic design, there should be robust, there should be process variation tolerant. In that case, there should be very less effect of the process variation. Whereas, let us move to the puff. In the puff, we are expecting that there should be some process variation so that I can get more randomness, so that I can get more unique challenge response pairs. So to get unique challenge response pair, if my requirement is to design the puff, definitely the process variation is kind of benefit. Similarly, if move to the TRNG, I was talking about the process variation gives you the random outputs, but if you want to make it completely random, noise becomes one kind of benefit. So if you have a noise inbuilt or added into it, this is one kind of problem, especially in the logic. But if you want to make the TRNGs out of the PRNG, noise becomes one kind of benefit. Similarly, for the counterfeited IC, aging effect. Aging means NBTI effect. Ultimately, I don't want any aging effect. Okay, but if you want to detect your counterfeited IC, aging becomes the benefit for it. So with this note, this is the end of the session.